In this video, we're going to continue our discussion of numerical differentiation. We will cover a brief introduction to non-uniform grids. In all of our previous discussions of finite difference methods, we were dealing with uniform grids. Here we will briefly introduce the idea of finite difference methods with a non-uniform grid. So in many applications, the function can vary rapidly in part of the domain and have mild variations elsewhere. In computationally intensive applications, it's considered wasteful to use a fine grid capable of resolving the rapid variations everywhere in the domain, but it may be of interest to have higher resolution in the region where the solution gradients are expected to be large, and lower resolution elsewhere. So we may want to use a finer mesh just in some regions. So consider a 1D case where we have points here, I-1, I, and I+1. And you can see the spacing between the points is not uniform. So delta x1 is not the same as delta x2. And let's look at how we can come up with an approximation for the first derivative at the node I, where this spacing changes. So using the forward finite difference approximation for point I, we can write the expression shown here up to the, including the third derivative term. So we have the error term here, order delta x2 to the power 4. We can also write the backward finite difference. So here we've got, we're looking at the node here, I and I-1 using the backward finite difference. And again, we have up to order, in this case, delta x1 to the power 4. So if we subtract these two expressions, 1 minus 2, we get what is shown here. And so the third derivative terms have been now grouped into the error term. So we're here with the error of order delta x squared, where delta x cubed, where delta x cubed is the higher of either delta x1 cubed or delta x2 cubed. And we can rearrange this for the first derivative, and we get the expression shown here. So now we're dividing by this term, delta x2 plus delta x1. So you can see that our error term has now become on the order of delta x squared. So the finite difference approximation for the first derivative can be taken as just the first two terms. So this becomes, or the first term, so this becomes the expression shown here. So df by dx at I is equal to fi plus 1 minus fi minus 1 divided by delta x2 plus delta x1. So we can see this again here. And now let's consider the order of accuracy of this approximation. So if we call this expression here star, this implies that this expression is second order accurate only if delta x2 goes to delta x1. So if delta x2 is close to delta x1, then that means that this term here will be small. And if delta x2 is equal to delta x1, then this term is equal to 0. So if this term is small, then basically that means that that the order of this term will be less than or equal to the order of delta x squared. So this term would be less than or equal to this term. So then the order of accuracy of our method here would be on the order of delta x squared. So it would be second order accurate. However, if the mesh size changes abruptly, so delta x2 is not close to delta x1, so say it's 2 times delta x1, then the accuracy at node I deteriorates to first order, because then in that case this term is not smaller than this term, and our error term becomes delta x.